Hey, good evening, everyone. Let me find out my slides. Yeah. I remember last time we probably stopped at transfer learning, right? The introduction to transfer learning. Okay. Right. Let's continue on today's lecture. So we were basically finishing this introduction part. Yeah. Okay. All right. So next, let's talk about very interesting topic, which is transfer learning. This is a technique developed not for kind of improving the development of deep learning models, but it is a technique introduced for addressing the computational burden in developing a deep model for a problem. Okay. So the main motivation of studying such. Let me see, someone probably is not on mute. Yeah, okay. So one major motivation of studying such kind of concept is that people find out every time when we want to utilize deep neural network to solve a problem or to deal with an application, we train deep neural network from scratch. That means from zero. Every time is actually troublesome. It's very time consuming and wasting efforts. So people start to think about, all right, in the world, there might be data sets which share some similarity or similar knowledge, or some of the developed models, they can have some overlap, okay? So can we inherit any of the knowledge in the neural network we have trained in the past to some new applications to save our training efforts? Okay, at least to save our electricity bill on the computing power, okay? Therefore, people are thinking about, can we have a very general deep structure which actually represent most of the cases and can be easily adapted into other individual applications? So basically, they ask, can we have a backbone model, very generalized, developed from a very large volume of data with a high diversity? Okay, for example, one one library ImageNet. Okay. Can we develop a very deep convolutional neural network for addressing most of the computer vision problems? We are using the big image library ImageNet. Okay. And if this can be realized, then the next question is, can we adapt this background model into different applications by just some very tiny operations? For example, slightly modifying network structure via just a limited volume of data. Or we can directly transfer by just refining or tuning again about the model structure. Okay. Therefore, a new paradigm of computing and utilizing data has been proposed. So if you remember, like in the past course, we're talking about in machine learning, the data organization is basically training, testing, right? And those kind of. For example, if we have a table, then we will have kind of one significant portion for training, and another significant portion for another small portion for test. Okay. This is the usual way we deal with the data and prepare it for machine learning tasks. Okay. And such kind of data preparation for machine learning task is usually fitting into a concept people call it single task learning. That means your data is just prepared for one application problem. Okay, you just prepare that data for developing a data-driven model for such kind of application. And what if we want to deal with kind of multitask learning problems? That means we develop one general model and next adapt it into different application problems based on their own small data. Then what will be changed? Then people propose a new paradigm of organizing data, which they actually grab a significant portion of training of part of the training data from different application problems and fusing them. Okay, assume that you have different number of tables, and each number of table of data sets is associated with one application problem, right? So you're taking a big chunk of the historical observation of different application cases and fusing them as one, aggregate them together as one data set. And such kind of data set is defined as source domain. Okay. And we denote the input pair XS and its targets YS as the to describe the pairs of records in the source domain. Yeah. So Actually, Chongjin, you have any problem? I saw you unmute yourself. Hi, Chunjing. Is that Chunjing? Yeah, please feel free to ask or you can type, okay? All right, so this is the source domain, okay? The source domain is an aggregation of a majority chunk of data points from the data set of different applications, okay? The input is denoted as the X and the output denotes Y, and we use a sign little s to denote that it is source domain data points. And such kind of aggregated data sets can also be split into training and validation part. Okay, so what they want to do is they want to just train a very generalized background model because you have very large volume and very diversified samples in the source domain. Okay, and after preparing the source domain data sets, and next we need to prepare is the individual target domain data set. What is the target domain mean? So target domains from 1 to k indicates the number of applications or the learning tasks from 1 to k. Okay, learning task from 1 to k. Or the real application problems that you want to solve from 1 to k. And each problem has its own data set, but with a very small volume. Okay, so those target domain data sets, they are utilized for fine-tuning and further testing the model developed from the source domain. Okay, so fine-tuning is a kind of adaptation process. You're adapting the background model into this target domain and then verifying its performance. Okay, so this is the data set arrangement in transfer learning. Then based on this type of data arrangement, then a number of transfer learning strategies have been developed. And the strategy one is very simple. So we use background model parameterized by the its weight W and bias B as an initialization. Then what we do in the adaptation, or what we want to transfer, is we want to transfer the whole network architecture, but just updating or fine-tuning the weights and the bias based on the target domain data sets. Okay. So this is very similar. It is very similar to the usual fine-tuning process. Okay. It's very similar to the fine-tuning process. Yes, the structure fixed, and what we need to do is based on new data, updating the W and B. The strategy 2 is a little bit advanced and actually introduce a certain flexibility in the way of dealing with transfer learning. The strategy 2 is called layer transfer. What does that mean? Its idea is very trivial. For example, given the source domain data, we build up a deep network with 1, 2, 3, 4, 5 layers, while the number of hidden layers are 3. Okay. And this is the deep neural network we build based on the source data. Okay. So if we want to transfer such kind of network to a new application, we can choose to transfer the whole architecture, or we can choose to transfer some of those very meaningful ones. For example, we transfer some of the hidden layers we learn, or hidden structure. Okay. So for example, here we consider to transfer the inputs in the first hidden layer, then using the target data to train in the remaining ones. Okay. So the remaining ones will actually grow based on the transfer ones as in initialization. And we develop new layers one by one from scratch and to the output layer. And after such kind of development process, then we fine tune all the things. Okay. Again, based on the target data, target domain data. This is called layer transfer. But you might ask, like, which layer I should choose to transfer? It is very arbitrary. Okay. It is an empirical choice. But sometimes people can decide, can make a reasonable justification by visualizing the feature map generated from the hidden layer. Okay. They will basically grab a sense that such kind of information until such kind of hidden layer is good to transfer. Okay. So there are some empirical observations, not the theoretically guaranteed knowledge. Okay. It's just some conclusions that obtained based on the previous experience. So people empirically will say, in the image processing applications, we usually will transfer first few layers. Okay. And in the speech recognition applications, we prefer to transfer last few layers. Do any one of you know why? Can any one of you have any guess on that? Why image processing prefer to transfer first few layers, while speech recognition prefer to transfer last few layers? It is actually analogous to the way human understanding information. Okay. For example, if you look at the image at the very first few layers, it's actually convolutional layers processing pixels. Okay. So in every image that you go to the pixel level, they are actually kind of similar stuff. Okay. They're just pixels, a vector of 5 elements. And by aggregating those pixels via convolution, or by convolving those pixels, we get a little bit abstract but high level features, which probably can describe some texture or patterns like edges, lines. Okay. Those are actually fundamental stuff to forming different objects, right? But if you go further, then that convolution will return the motif or more advanced features that will be specific to different types of applications. Okay, so the later knowledge becomes specific towards some applications, but at the beginning layers, they are general, so they are transferable. Okay, in the image processing using convolutional process. But in the speech recognition, if you guys hear what I talk, I have accents, right? And you guys too. So when different people read the same sentence, they have different accents. They have, different tones, okay? But if you extract higher level knowledge or higher level features from the speech signal, they becomes phrases, okay? More abstract, but more close to be understandable. Okay, and at that level, those features are general to express the meaning of the sentence you're talking about. Okay, so this is the language processing working flow. Okay. So layer transfer. So the third is called feature representation transfer. So it is a little bit more complicated. It talks about like using source and target domain feature spaces to identify a latent representation, which offers a generalization of relationships of latent variables mapped from various source and target domains. What does that mean? Let me draw some graphs so that you guys can understand. Assume this is target domain, okay? And this is source domain. So we use target domain to generate a kind of deep neural network. And we use the source domain to generate another set of neural network. This target domain problem is different from the source domain problem. Okay, problem different. But there's a possibility that you can have a latent features which can be reusable. Okay. For example, the structure of the latent features from its previous layer, okay, connecting to these latent features. So these latent variables, they are actually domain invariant. We call them domain invariant. That means there are a set of features can be generally utilized in a number of different domains, okay? Or in another way, assume that you are training deep network for different domain problems. But you will have one hidden layer, they are domain invariant, which can be utilized across different domains, okay? And such kind of feature representation from the beginning input to the latent features, they are able to be transferred. Okay. All right. So this is a very basic idea of doing transfer learning. So there are different ways of doing transfer learning. We can do just instance-based transfer. That means we're just fine-tuning the structure of a developed backbone model based on the target data set. Okay. Or we can select some of the architects from a whole architecture to be transferred. Okay, that means it's kind of pruning some of the tree and replace such kind of tree in other tree model. Okay. Remember, when we talk about the tree model, we talk about that we can replace some of the structure in the tree with some frequently used one. Okay, frequently used ones. And the last one is called feature representation transfer, which means we can develop one latent layer, which is domain invariant. Okay, and such domain invariant latent features can be utilized as an input to developing further machine learning models for different tasks. Okay, so that's the transfer learning. Okay, so we finish these slides, and next we are going into some of the application studies with data science. Okay, so the first set of applications we're talking about is the data analytics in nowadays a very famous renewable energy called wind energy. Okay. So why we select wind energy as the first application topic to talk about? Definitely, this is due to our recent worldwide initiative, which is very ambitious, which is called carbon neutrality, okay, or zero carbon emission society. This is the very important plan to help people living in this earth to react to our climate changes. Okay, so if you guys pay some attention, then you will know that in past 2 years, extreme weathers have happened around the world more frequently. Every time we face some disaster, we say that it's kind of happened once in 100 years. Okay, so we frequently talk about this is 百年一遇 or kind of 千年一遇problem. But how come those 百年一遇climate issues or natural disaster happen so frequently? Not just in mainland, but also in United States, in other places, in Europe. Okay, this is indeed our climate has been changed. Okay, the Earth dynamics has been changed, and this backfire has propagated back to our daily life, and some unexpected events are going to happen, and people need to be well prepared. So renewable energy as wind energy is one of the two mostly successfully commercialized renewable energy. Another is solar power. Okay, so they actually play a very important role in the city sustainability. Okay, they are actually clean. Their generations does not induce any carbon emissions, and their system architecture is very unique. So if you guys look at wind farm, okay, it is composed of a population of distributed unit. Let me show you guys one figure. So if you guys look at this stuff, they're actually wind farms. So they have very big machines. So they're composed of a population of actually distributed units. And these units are very difficult to manage due to the following reasons. The first one is those machines, they are working exposed to wild environment, to the wild, okay? So they are facing rains, strong sunshines, extreme cold weathers, okay? So they're going to be damaged by the weather anyway. So they are working in a very hostile environment. And the second is the natural resources such as wind and sunshine, the solar radiation. The solar radiation is a little bit more certain, but wind is actually completely uncertain. Okay, so you have strong uncertainty. And the wind energy asset, so every wind turbine is very expensive. So we want to be careful on them, okay, on them. Otherwise, their damage could cost in million level, okay, million Hong Kong dollars. But the good thing is the wind turbine has some new features. So it is designed and manufactured to be fully instrumented. That means the installation of wind turbines will be going with a lot of installation of sensors. So a lot of data on wind turbines will be collected. So this is an image of a commercial wind farm. Okay. Then next, let's understand some domain knowledge. The wind turbine system. What has been included in wind turbine system and how does it generate power? Okay, for supplying our daily electricity usage. So the main components of a wind turbine is offered on the right. It has some very big components like wind turbine blades. So this blade could be like 50 meters or even longer, depends on the capacity of the turbine. And the rotor is also very big, okay? And inside, the big guys includes, one is the brake to slow down, to introducing torque to slow down the rotation of the wind turbine rotor, okay? And the gearbox. So what is the function of this gearbox? Why we need to have a gearbox here? So if you look at these big blades and rotor, when wind blows over here, it rotates, but with relatively a lower speed, okay? But this lower speed is generated with a big mass, okay? It has a lot of energy. So we need to use a low speed gear to drive another smaller but a high speed gear, okay? And this high speed gear will lead the drivetrain to rotate the generator with a high speed, okay? Then after the generator is rotating, then the electricity can be produced, okay? Then the whole bunch of stuff is contained in a box called Nacelle. Okay, Nacelle is this whole bunch of box containing those gears, generators, drivetrains. There's a controller to control the wind turbine blades. There are two things can be controlled. One is the angle of the blades. Another is the brake to introduce the torque to be controlled. Okay. So this anemometer is a sensor. It is utilized for measure the wind speeds that the wind turbine is experienced. Okay. Good or bad? The bad thing is this anemometer is usually installed on the back of the nacelle. That means you are just able to measure the wind passing through the turbine rather than the wind approaching the turbine. Okay. This is simply because the turbine will rotate, and if you install it on the front, and it will be hit by the blades. Okay. All right. Then we have different directions, and what we want to control the wind turbines is that it always faces in a perpendicular direction. Okay, make the space that the blade swapped be perpendicular to the wind direction. Okay. Then to control the direction that the nacelle is facing or is attacking, we need to rely on another system, which is called yaw system. So there will be a power to supply electricity to drive the yaw motor, and there's a yaw drive to rotate, okay, to change the direction of the nacelle is attacking. So there's a power cable which connecting to the generator and to the ground, okay, via this tower. Then this power cable is gonna to supply electricity to the grid. But there's one thing, most of these renewable systems, renewable energy systems, they are generating DCs, okay, not ACs. So there will be a DC to AC converter installed on the ground to convert the electricity from DC to AC, then integrate it into the power grid. Okay. So we know that the wind turbine itself is a very complicated system. It is composed of a large number of mechanical and electrical components. And its energy conversion process is highly nonlinear. It is because the wind speeds we don't know, and its energy conversion process is first. We'll have slides in the later to talk about how it is converted energy. So let me introduce some basic idea of how the energy is converted to power with a wind turbine. So first, the wind is blowing, okay? The wind is blowing, that means the wind carries the kinetic energy, okay? Which drives this rotor to rotate, then which the kinetic energy is converted to mechanical energy, okay? And this mechanical energy drives the drivetrain to rotate via the gearbox, finally to the generator, and it becomes electrical power. Okay, definitely you will know that energy conversion from one stage to another, you will have an efficiency. Okay, such efficiency is usually determined based on the design of the system. Okay, but it will also affect by the quality of the system produced, as well as the controller, okay, installed. So the whole conversion is highly nonlinear, and it involves a high dimension of system parameters. So a lot of parameters will be measured on this system. including the voltage and current, okay, of the electricity generated, the wind speed, okay, and other outside sensors to measure the temperature, the weather condition. And inside the nacelle, you have temperature sensors to measure the temperature. Okay, you have accelerometers to measure the vibration. Oh, yeah. And you have sensors to measure the generator torque, the angle, the blade pitch angle, the generator speed, the rotational speed of the gears, the rotational speed of the rotor, the yaw angle, okay, and so on. So you just have like very high dimension of system parameters, and usually like it's higher than 100, okay, dimensional parameters. But the good thing is the wind is replenished by the nature, but in a stochastic way. But anyway, it is free though. Okay, the wind is free though. So to manage such kind of distributed big machines, we cannot just do our traditional practice of management that we visit area of the machine and check its conditions and see whether we need to do any maintenance. We cannot do that. There will be more than 100 wind turbines in a wind farm, and they are distributed in a very wide, in a very broad area. So if you even you drive a car to visit turbine one by one, finish a whole wind farm probably already take you 1 day without any checking. Okay. So what we need to do is we can install an IoT system to collecting data from those of the distributed systems. And such kind of system is called supervisory control and data acquisition system. Okay. Or sometimes we call SCADA system. So this SCADA system was originally designed for monitoring wind turbine conditions. But meanwhile, it collects a massive volume of wind turbine data. Okay. So originally what people pursue is, okay, I could collecting data of many dimensions, and I set some threshold. And if those threshold is crossed over by some signal, then we receive some alarms. Then we need to take reaction to do maintenance or to do checking. But after the development of the machine learning techniques, people realize that such kind of massive volume of collected wind turbine data, they contain a huge value, okay, which can be further developed to benefit the wind farm operations and management, right? So basically over 100 systems and environmental parameters involved in wind power generation process are measured, okay? And next, in the collected data, what we want to understand more is about the sampling frequency. That means how frequent we collect the record for that parameters. So the sampling frequency can be pretty high if the installed sensors on a wind turbine has such kind of capability. But collected data, they are typically stored in a 10 minutes interval. And it is simply due to the storage constraint. Okay. Even such kind of 10-minute interval data, you already been huge. Okay. So we have an experiment. If we take very high frequency data for recording kind of drivetrain acceleration on a wind turbine for 10 minutes, such kind of data set is already rich kind of 10 gigabytes. Okay. So we have to condense the frequency of sampling to save our storage space. Okay. And such kind of collected SCADA data, they actually enables the era of wind energy big data analytics. Okay. All right, so we stop here and take a 15 minutes break. Then we come back and continue our story. All right, let's come back. So actually, the SCADA system I have introduced previously is more like kind of IoT technologies. It's one very standard industrial IoT example. And now another very standard IoT example nowadays is the vehicle internet, okay, or internet of vehicles. So what they collect is your battery data. Okay, so the battery data will be collected from individual vehicles to the central cloud. Okay. So based on these IoT systems, we are able to producing a large number of large volume of data from such kind of distributed systems. Then we're using such kind of large volume of data. What kind of wind energy problems that we can solve? So actually, these problems that to be solved from the data-driven aspects, there'll be two groups. Okay. So the first group is related to problems only involve machine learning techniques. For example, the uncertain factor forecasting, such as the wind speed, wind power. And the second is the data-driven wind turbine modeling. Okay. Another set of problem is actually a little bit beyond so-called machine learning. It's kind of machine learning plus. So it's basically machine learning plus another field technology, for example, machine learning plus control. So related to data-driven wind turbine intelligent control, or machine learning plus scheduling, then that would be a data-driven wind farm operations. Machine learning with condition monitoring techniques, and that would be data-driven wind turbine condition monitoring. First, let's look at the wind energy machine learning problems, the group of the problem. In wind energy machine learning, or we call wind speed power prediction problem, as well as the wind turbine system model. So we have a more abstract figure illustration of the wind turbine system. We have the blade rotor here, gearbox here, generator here. This is a brake, and also the grid and the load and an energy storage tank. Okay. So a data-driven modeling process actually considering physics-based and mechanical principles. So it is needed that we incorporate the domain knowledge into further studying the data-driven modeling. At least from the domain knowledge, we will know factors related to such kind of process and who should be considered as inputs and who are the output generated by some axis. Okay. Based on the domain knowledge, then you need to know system inputs and the outputs. Okay. And in wind energy application, the inputs have two categories. One is called controllable parameters. Another is called non-controllable parameters. What are controllable parameters? Those are, for example, the generator torque, blade pitch angle. Those can be controlled by a controller. And what are the non-controllable? That will be related to system conditions and the environmental conditions. For example, the temperature, the wind speed, and the weather condition. Okay. And the output parameters, okay, they can be numerical or categorical based on the definition of the problem you would like to consider. So we can bring our earlier talk system engineering idea here for studying the wind energy machine learning problem. Basically, the first step is we need to rely on the domain knowledge to identify the X and Y we would like to use. Who will be regarded as the inputs and who are the system outputs? Okay, then we are actually mapping the relationship, learning the mapping between the inputs and the outputs, okay, which actually approximating the true system dynamics. So X, Y are actually known as data, while the function needs to be obtained. Okay, so given a loss function L, a data-driven system modeling task typically aims at identifying a non-parametric model GA via algorithm A by minimizing the loss between the estimated Y via GA using X and the true observed Y. Okay. So two types of problems can be generalized under the same computational framework, including the prediction and modeling. Okay. So the differences typically include the considered input parameters and the output parameters. So basically, in the modeling problem, we're actually doing estimation of the power output YT based on the system condition and control parameters applied at time t, which are the input, described as X. And in the prediction, we're actually using the inputs observed at t to forecast the value of the future power output, which is yt plus n, where n is larger than or equal to 1. So overall, the learning process can be the same. So which is just to find the function correctly describing the relationship between x, y, and based on data. So one early work and very milestone work in wind speed and power prediction studies using data-driven approach is published by these three authors. So they actually propose a very flexible data-driven approach, which break the very classical time series, the constraint from those time series forms, like autoregressive model. You have to formulate them as a very rigorous and parametric mathematical form, right? So, but here, what we want to do is we just approximating the historical states of the power output and its future generated value, okay? So we select a number of historical states of Y as the input and select the future observed Y as the output, and we develop mappings among them. This is a data-driven time series, although it does not involve any exogenous variables, that any axis other than Y's. Okay, so one thing I would like to supplement is this X in prediction, they might not always refer to some control or non-control variables. They were non-controllable parameters. They will also refer to the historical states of the Y itself. Okay, it can integrate the time series into it as the input, or just time series as the input too. Okay. So the problem is, in such kind of problem, how to select appropriate input parameters for doing data-driven modeling. For example, the features. Here we know that based on one signal, we will have a long history of its records. Okay. Then what are the historical states we need to select? Or what historical states have a big impact on its future value? We don't know. We have to do the data mining to discover that. Okay. So how to select the appropriate input parameters for doing data-driven model, and how to select the appropriate algorithm for developing and learning the data-driven models. To address the first problem, we already know that we can use some feature selection strategy. Okay. So we have talked about different way of doing feature selection. One is based on the domain knowledge or based on the principles. For example, we can study the aerodynamics models for wind turbines. Then we will know the key parameters in the aerodynamics that will affect the output or the target variable, which is the wind power output. Okay, or we can heuristically or exhaustively try and error process, which that means given a set of features, we just iteratively incorporate those features as the input to do the regression. Then we evaluate the contribution of this input into the improvement of the regression performance to decide whether we need to retain it or we need to exclude it. Okay. Or we can use some linear models with feature selection capability. For example, Nacelle, okay, which is able to generate a set of significant parameters from the linear relationship aspect. And if you have a special concern on some nonlinearity or nonlinear relationship between the input to the and the output, we will also use some analytical strategy based on some of the models. For example, we can use the boosting tree. It offers a kind of importance rank of the parameters. Okay. Or based on the neural networks, we can do global sensitivity analysis to decide the important parameters. Okay. But there's no theoretical guarantee of the global optimal choice due to two reasons. First one, the features measured in the existing system, they might be insufficient. Okay. So they might be just a kind of subspace. If you have a more complete space to do the feature selection, results can be different. Okay. The second is that the feature selection and modeling algorithms can be different. For example, your feature selection is based on one type of model, for example, boosting tree. But when you want to do a regression between the selected features and the output, you probably will go to NN because NN has a better performance, right? And actually, your feature selection is not based on NN. Actually, it's based on boosting tree. So those kind of feature selection, we usually regard them as some empirical suggestions, although it is the results are derived from some data mining or machine learning algorithms. All right. And next, after we have selected those features, we need to determine the algorithms for doing model. Okay, for doing modeling, data-driven modeling. Then how can we do the algorithm selection? For example, we have neural network, we have support vector regressor, we have regression trees, and we have regression spines. Okay, then which one we should choose? So a pool of candidate algorithms need to be determined. This is the first thing. You need to determine who will be considered in such kind of selection, or who are the suitable algorithms for doing such kind of task. Okay. So if it is the regression problem, so you will probably consider some of the algorithm which has been most widely utilized in different applications. Okay. Then you conduct computational experiments for comparative analytics. You compare them, see which one is better. And such kind of comparison needs to rely on some of the assessment metrics, such as MAE, MSE, MAP, like mean absolute error. So So let me explain the abbreviations. MAE actually means mean absolute error. MSE means mean square error. MAP typically mean absolute percentage error. Or sometimes people will use another word called relative error, okay? And as well as the standard deviation of those errors, like standard deviation of absolute error, standard deviation of square error, and standard deviation of absolute percentage error, okay? And all computational should be conducted on training data set. And training data set can be split into training and validation, okay? So next, actually the whole regression or prediction idea can actually be more inspiring, okay? So it can be beyond just a kind of prediction, right? So for example, what we can do, first, we have the current and measured wind speed, or past or predicted wind speed. And we can do a prediction of the wind speed time series first, time series prediction model of wind speed. Then we can do the predicted future wind speed. But this wind speed is not equivalent to power yet. Then what we can do is, in the data set, we have observed a large volume of wind speed and its associated wind power, okay? Then what will be interesting is we can apply K nearest neighbor to do what? We can apply the K nearest neighbor of the predicted wind speed and take the average of wind power of those nearest neighbors as the forecast. Okay, then we get the wind farm power. So the tricky thing is we don't do the direct forecasting again based on the wind speed to the power. Okay, we do the historical search. This is a kind of interpolation, right? So this is one interesting way. First, we use time series to forecast the future wind speed. And next, based on the forecasted wind speed, we search the history records, okay? Then do an average of what we have observed in the history. We believe that this has an assumption, okay? Or we have presumed that the future will, the historical events will also happen in the future. Okay. So such kind of idea is very novel. So I would like to introduce this story is that please don't bound or don't limit our mindset by the very standard classical data analytics process. For example, data preprocessing, feature selection, and then just do the modeling, right? So there are some other very creative way of doing data analytics, but what you need to understand is you need to have a deeper understanding of the principle of the algorithms. All right, and next, so some illustration of the results. This is obtained from that paper. So authors applied 5 algorithms, including the support vector machine regression, multi-layer perceptron, and M5P tree. The remaining 3 are just the trees. The tree with different training mechanism. Okay. So the right side is an illustration of the prediction performance. The red dots, they are observed values, and the black dots, they are predicted values. So they are very, very close. So to determine which one is more suitable, we will first look at definitely the magnitude of the errors. So the lowest one will be preferred. Okay, so here probably support vector machine regression will be considered as a good one for doing time series analysis. And the second one is the stability of the error. So we will measure its standard deviation. A low standard deviation indicates the performance, the error changes are more stable. Okay. So previously we talked about the KM-based integrated prediction model. Then for doing, okay, the new data coming in, then we need to divide the data into X and Y, okay, and compute the distance of the new data to the past record of the whole data set based on X. So this distance will be utilized to find out nearest neighbors, okay? Then next, we will identify the number of nearest neighbors we want to find, or number of nearest historical records close to X. Then we average their prediction of Y's, okay? So this is basically the mechanism of the KM. But the disadvantage is its online implementation is a little bit tricky if your data set has many data points, okay? Because the search process will be very time consuming. So time series models, we have talked, they actually only consider past records of the same parameters. For example, the inputs will be just the historical records of the target Y, okay, in that paper. But for the power generation process, besides its past records, or from physics aspects, we call there the system dynamics. Okay, beside the dynamics, okay, the other exogenous inputs like the controllable parameters you have applied, the control settings you have applied, as well as some external conditions, might also contribute into the future states of these target variables. Okay, we can actually extend such kind of acts by incorporating them. But be reminded that if you want to do a modeling, the value of those parameters, they should also be historical as well. For example, if you want to predict Y at t, and all the others must be observed at t-1 or even in the past, okay? All right, so we have finished the part 1 of this wind energy application. Then next, let's go to the part 2. So part 2, we will talk about the data analytics for characterizing the wind variations, okay, or characterizing some properties of some parameters. So characterization of some parameters is of importance to the wind industry, like for example, variation of the wind speed. This is very important because it has a number of following benefits. First, designers can use the results of such kind of characterization to optimize the design of the wind turbine systems. For example, the design for minimizing the energy generation cost. Or the wind farm designers can use such kind of characterization results to determine the location, potential location of that wind farms, and the locations for put down the wind turbines. Moreover, the energy asset investors, they can use such kind of characterization to estimate the income from the electricity generation of that energy asset. So how to characterizing the wind variations? And the first choice is that we can use the statistical distribution. And one very famous distribution is called Weibull distribution. There are a number of reasons for choosing Weibull as the distribution of the wind. One is by plotting the historical diagram or histogram of based on the wind speed observations obtained in the past. Its shape of the histogram is naturally close to what Weibull distribution shape. Okay. And the second reason is the Weibull distribution has a kind of high freedom high flexibility on its shapes. It has a number of parameters to determine its shape. Okay, so it has a flexibility to change its shape based on changing its parameters. So based on the general pattern of wind speed variations, the Weibull distribution is selected, and it can be utilized to describe the wind variation for a typical site. So one location, the wind variation will be summarized via one Weibull distribution. And in this figure, we can see that the site has the mean wind speed of 7, okay, of 7 here. And the shape parameter of the function is k to the 2, and the data has been collected over a year period. So the mathematical description of a Weibull distribution is like this. So the x is the input, basically the wind speed. There are two parameters to control the shape of the Weibull distribution. One is ky, another is lambda. And this Weibull distribution belongs to an exponential family because it has an exponential term like Gaussian has. Okay, and the lambda larger than 0 is the scale parameter, and k larger than 0 is the shape parameter of the distribution. So for k equal to 3.4, the Weibull distribution appears similar to the normal distribution, but for k with a value 1, the Weibull distribution becomes the exponential distribution. Okay, so this is some review of the Weibull distribution. So this is a visualization of the shape of Weibull distribution with different pairs of lambda and k. Okay, so the red line means the shape of the Weibull distribution if lambda equal to 0.5, k equal to 2. Okay, then the green and purple and the pink lines actually reflect the shape of Weibull distribution with other pairs of lambda and k. The median, mode, and mean of the Weibull distribution are described as follows, as the right side equations. So some description of wind speed based on such kind of Weibull distribution. First, the area under the PDF curve is always exactly 1. So this blue area, okay, its whole sum is 1, which indicate the probability that wind is blowing at some wind speed, including 0, is 100%. Okay, so this distribution can include all kinds of possibility of wind speed. The median here is 6.6. Okay, the median is 0.66. It includes that half of the blue area is to the left. Okay, and this means that 50% of the time the wind speed is less than 6.6 meters per second, and the other 50% of the time the wind speed is greater than 6.6 meters per second. Okay. And what we want to know is that the median is not equal to the mean, right? The median is the median, the mean is the mean. The statistical way of getting that value is different. Okay. And the mode, the highest place is actually pointing to 5.5 meters per second, which is the most frequently observed wind speed. Okay. So most frequently you observe that wind speed is at 5.5 meters per second. And the statistical distribution of wind speed depends on the location, the climate conditions, the landscape, and surface. Okay. So although we have the statistical distribution records, but naturally from the natural conditions, the physics aspects, we will know that the location, climate conditions, and landscape and surface actually both contributes to such kind of distribution of wind speed. So the Weibull distribution may thus vary in its shape, determined by the PDF parameters. Okay, so if you change the location, or change the climate condition, or change the landscape and its surface, you have to re-estimate the Weibull distribution by re-estimating the previous we talked the lambda and k. So this is very simple statistical analytics or very basic data analytics, but it is very important. Okay, so we can see that based on just simple analytics, we can tell a lot of story from such kind of visualization. Okay, and this actually insights actually tell us a lot of information, basically the resources here and whether it is deserved to build up a farm, and whether you will what is the economic benefits if we build up a farm here. So if we extend from the wind speed to the energy scale, and we have to touch this average bottle fallacy. Okay, so from the wind to the energy, it's V cubic. Okay, So its shape will be like this. So the average energy content of the wind at the turbine side cannot be determined from the average wind speed. Rather, the Weibull distribution is needed. Okay. Why the average energy content of the wind at the turbine side cannot be determined from the average wind speed? We explain next. We use a bottle as an example. So how large is the average bottle? Here it is two. One, for example, one is 0.24 meters. Okay, and no, this is not meter. It's just 0.24 mil. Okay, and the other is 0.76 mil tall, and both are of the same shape. Okay, the one is only 3.17 taller than the other one. Its volume is actually cubic. Okay, so if we calculate the volume, it's cubic. So we cannot just use an average to do the estimation. Okay. Next, we want to talk some physics behind or physics guide the computation of the wind power generation, okay, which is called Bat's law, which is the ideal breaking of the wind. That this Bat's law actually offers the theoretical upper bound that the kinetic energy can be converted. Kinetic energy from a wind can be converted to the electricity power. Okay, it's upper bound. So the more kinetic energy a wind turbine extracts from the wind, the more the wind will be slowed down. Okay, so for example, if you have a strong wind come over here from the right to the left, but after rotating, after the energy extracted by the turbines, then the latter V2 will be much slower. Okay. And an attempt to and what a wind turbine attempt to do is to extract all the energy from the wind. A perfect machine aims to extract all the energy from wind, but it is impossible, right? But if it is in the ideal case, it will reduce the speed of the wind to 0. That means you absorb all the energy and there will be no wind afterwards. Okay. And this is too ideal because this indicates that the air could not leave the turbine. In that case, we will not extract any energy at all, as the new air would obviously be prevented from entering the rotor of the turbine. And the passing air without speed change will lead to 0 extracted energy. Okay. So the optimal point is an ideal wind turbine slows down the wind by 2/3 of its original wind speed. That means make the V2 equal to 1/3 of the V1. So the Bat's law presented in year 1919 says that one can only convert not more than 16/27 or higher than 59% of the kinetic energy in the wind to mechanical energy using a wind turbine. Okay. So this is presented by Albert Batz, a German physicist. Okay. The modern rotors achieve value of the coefficient of a performance which is equal to 0.4 to 0.5. So this is pretty high already, okay, and which is already 70 to 80% of the theoretically possible value, which is 0.59. Okay. And there's a drawback of the Bat's law if you look at this figure. So this green line is the Bat's law we have drawn. Okay. So if we want to operate a turbine by maximizing its performance to achieving the boundary the Betz law presented. There's a problem. First, the Betz law approaches a rated wind power too early. Okay. And this part is too theoretical, too ideal. But in the left tail part, in a low wind speed condition, the Betz law actually kind of cross over the cutting wind speed. Okay, so it becomes slower. So there's a crossover point that the theoretical control needs to rely on another bound. Okay, the dynamics have been changed. So this is some of the discovery of the insufficiency of the Betz law based on the data analytics. All right, so next we will talk about the so-called power density function. So the power of the wind will be described by this equation highlighted here. This is based on the aerodynamics. So the power will be equal to 0.5 multiply L density rho and multiply A, capital A, which is the swapped area by the wind turbine rotor, and multiply V cubic. And there should be another capacity here if converted coefficient here if the power is converted from the kinetic to the next stage. But this one is the pure power content or the kinetic energy content in the wind. So we don't multiply any coefficient here of conversion here. Okay. All right, so how about we stop here and take a break and come back at 9 to continue. Okay. Okay, let's come back. Right, so we are now staying at the description of the power density function from the physics side. Then we will basically start with this, start from this point and to see how the physics talking about modeling the wind power generation process. And next, what is the shortage or the shortcoming of the physics-based approach, and what will be the advantage of the data-driven approach. So we talk about this gray area actually describe the power of the wind. That means the energy content in the wind, ideally power included in the wind. Okay, but after the rotor rotation, the kinetic energy content in the wind is converted to the mechanical energy. Okay, so the area under the blue curve shows theoretical power that can be extracted in a perfect way. And the total area under the red curve represents the electric power a certain wind turbine could produce. Okay, this is the more realistic one. The blue is the theoretical one. Okay, so the turbine's power curve determines the actual power produced. Okay, then we will see that. So the whole wind turbine system efficiency will be equal to a multiplication of 4 types of efficiencies. First, the efficiency at the rotor part. This efficiency describes the efficiency that the kinetic energy can be converted to the power ideally can be absorbed by the wind. Okay. Then the second is from the rotor to the gearbox part. The rotor drives the drivetrain, and the drivetrain drives the low-speed gear, and this low-speed gear drives the high-speed gear. Then the high-speed gear drives another drivetrain, which is leading the generation of the generator. Okay, so this gearbox has a kind of mechanical energy conversion, which introduces another efficiency. And the next one is the mechanical power converted to the electrical power via the generator. But does that the final outputs that the power can be supplied to the grid? No. The last step is the power converter. As I said, the renewable energy systems, they are actually output DC. Okay, they need to have a converter to convert DC to AC to fit into the power grid. Okay, so there will be the last stage, power loss, efficiency loss. Okay. So we know from the physics or from the domain background, the whole energy conversion process. Now we talk about the wind turbine modeling, first from the physics aspect. So wind turbine modeling majorly talk about modeling the wind power conversion process. Okay. So there have been a number of ways for modeling such kind of process. They include the computational fluid dynamics, or more specifically, the aerodynamics. Okay. And such kind of study is done more from the design stage, okay, more simulation-like, to roughly estimate the extreme capability of a turbine. The second is from the power curve model. The power curve model actually describes a binary relationship, which a biparty relationship, which is between the wind speeds and the power itself. It is an extremely simple model to estimate the power output. It's easiest to compute. And the middle one is called data-driven model. It actually approximates the true aerodynamics from the data. We know that the physics model has a lot of assumptions. Okay, so the true dynamics may not be as described as in the in its such kind of mathematical formulation. But based on the data collected, we are able to track the real dynamics in operation. So first, let's look at the computational fluid dynamics model. Okay. So it is It is a kind of a subset of the computational fluid dynamics, which is the aerodynamics model, utilized to describe this wind energy conversion process. This formula describes how the kinetic energy in the wind convert to the wind power. Okay. So it involves a number of terms. First, 1/2, which is a constant, and this rho describes the air density. I guess the next slides probably have the individual of them. Yeah. So the P is the mechanical power produced by the rotor, which is here. And 1/2 is a constant, and rho is the air density. And the capital A is a rotor swept area. And Cp is the power coefficient. Its input is lambda, which is the tip speed ratio. And this V is the wind speed. Okay. And this tip speed ratio is equal to the rotor radius multiply the rotor speed divided by the wind speed. Okay. So if we visualize the mechanical power generation, its relationship between the power coefficient and the tip speed ratio in a 2-dimension, it will be look like this. But if we visualize the rotor power and its relationship to the rotor speeds and the wind speed to a 3-dimension, then it will be a curvature contour like this. Okay. So basically, we will find out a best rotor power output, which here. Okay. So based on different levels of wind speed supplied by the nature, we need to determine the best rotor speed, okay, to obtain the maximum rotor power. Okay. And this is how the nonlinearity comes from. Okay, it's highly nonlinear. So it is important to notice that the bulk of wind energy is extracted at wind speeds above the average wind speed. Okay. So if we take the average wind energy is extracted at some wind speed, and is above the average wind speed. And this is due to the fact that the energy content of high wind speed is much higher than the energy content of low wind speed. Okay. Basically, the nonlinear relationship between the power and the wind speed. Okay. The cube relationship. So we will find out in computational fluid dynamics model, there's one term which is implicit, which is the Cp, the power coefficient. It does not have an explicit mathematical formulation. Okay. And this one is highly nonlinear and does not have exact form. So naturally, it needs to be fitted from some of the data. Okay, it needs to be estimated. So such estimation can be done based on data, can be done based on control theory, and can be done based on stochastic process. And we will talk about the way of doing such kind of description we're using data. The first one we want to look is the power curve model. Okay. The power curve model is a concept which will be supported by the real data. So on the right, on the left side figure, it's a kind of ideal power curve usually offered by the turbine manufacturer. It's an abstract description of the relationship between wind and the power output. So there are a number of critical concepts, which is the wind speed term. Okay, there will be 3 wind speed term. One is the VC, which is called cutting wind speed. So what does the cutting wind speed mean? This is simply because if the wind speed is too low, it cannot drive the rotor of the wind turbine to rotate, right? So it needs to be strong at a level so that it can overcome the inertia and trigger rotation of the rotor of the wind turbine. Okay. So every wind turbine in its design, it has a cutting wind speed, and usually it's 3.5 meters per second, or some larger capacity wind turbines will be 4.5 meters per second. But a good design of the wind turbine wants to push the cutting wind speed to be smaller, the better. The smaller, the better means if your cutting wind speed is smaller, then you have a higher chance to operate. Okay, you are able to accommodate lower wind speed to generate power. All right. Another concept is called rated wind speed. The rated wind speed is a concept that describing that if the wind speed is higher than a certain level, the power output will reach its rated power, which usually is its maximum capacity. So what does the maximum capacity mean? Maximum capacity is the maximum power that can be generated by a turbine model. Okay. So any design of a turbine will have its technical specification on the maximum amount of power it can be generated. But can it generate more? It is possible. Okay. But it will drive the turbine to be broken easily. Okay, because it's overspeed. Okay, rotating too fast, faster than its design specification. Okay, so that could be leading to disaster or faster degradation of the mechanical components. So we try to control the turbine. If the wind speed is higher than rated wind speed, we want to control the turbine to maintain its power generation at the rated power. Okay. And the last one is called cutoff wind speed, which is VF here. What does cutoff wind speed mean? Cutoff wind speed means if the wind speed is higher than a level, higher than that cutoff wind speed, the wind turbine will be forced to shut down. Okay, to prevent some catastrophic disaster if the wind is too strong, like a typhoon or some others. Okay. So this is some fundamental knowledge, domain knowledge. Okay. And the right figure is the real data supported wind power curve. So you can see the biggest difference is the left figure, the power curve is like a line, but the right figure, the power curve is a scattered plot of data points. Okay. So why there are so many scattered data points? This is due to caused by the nonlinearity and some other events, some other factors. Okay. So this also indicates we can use a wind speed to roughly estimate power based on this line, but this is not accurate because the real power is like this. Real power curve is like this. Okay. There are a lot of deviations. So the power curve of a wind turbine actually plots the electrical power outputs at different wind speed. Okay. So the cutting wind speed and cutoff wind speed we have explained. So the most of the turbine typically set the cutoff wind speed to 25 meters per second. Okay. So if you operating wind turbines in a wind speed higher than 25 meters per second, it is possible that it rotates too fast, and the nacelle will drop down to the ground from the tower. Okay, it will cause mass imbalance and other issues. So we have talked about the different concept of the wind speed intervals. From 0 to cut-in, this is the area that there's insufficient power to overcome friction and initial torque. Okay, and the B, the interval B of the wind speed indicates the turbine needs to be optimized to be operated by maximizing its efficiency. Okay, and this is usually controlled. This area is usually controlled by controlling the blade pitch angle. Okay, and the C area, which is a fixed rated power output, and this also needs to be controlled. It is controlled by the generated torque, okay, to slow down, okay, the rotation. All right. So in plotting the power curves, we know that if the wind speed is not fluctuating too rapidly, then one may use the wind speed measurements from the anemometer and read the electrical power output from the wind turbine and plot the two values in the form of the power curve. But in practice, the wind speed always fluctuates. It's stochastic. So one cannot measure exactly the column of wind passing, and therefore one will see a swarm of points dispersed around. Okay. And furthermore, the actual anemometer error can be 3%, and these leading to 9% or even 10% higher error of the certified power curves. Okay. And this error amplification is typically leaded by this cubic term. Okay. This cube term, sorry. So this is figure illustrate actual power curve, and another figure visualize the real power curve. You can see that there's no certain pattern. It's very dynamic. Okay. So we need to verify the power curves. So power curves are actually constructed using the measurements in areas with low turbulence intensity and with the wind coming directly towards the front of the turbine. So the power curve can be utilized to verify whether the turbine is in normal status or not. Okay. So local turbulence and complex terrain may mean that wind gusts hit the rotor from the varying directions. Yeah, it may therefore be difficult to reproduce the power curve exactly at any given location. Next, let's look at the term power coefficient in the aerodynamics model. So power coefficient actually indicates the turbine efficiency, and such efficiency means the efficiency of generating power. And the power coefficient indicates how efficiently a turbine converts the wind energy into the electricity. The equation we have described in the past. Okay. So the power coefficient is equal to the electrical power output divided by the wind energy input. Okay. So the wind energy inputs like this, and the power coefficient is like that, and the energy varies with the wind speed. Okay. So there's an example. If a turbine was designed for the max efficiency of 44% at a wind speed of about 9 meters per second, then the efficiency is not as important at low wind speeds, as there's not much energy to harvest. But at high wind speeds, the turbine wastes the excess energy above the cutoff wind speed. So efficiency therefore matters most in the regions of the wind speed where the most of energy to be found. Okay. So the actual energy output from a turbine. So based on the different K of the Weibull distribution, we will estimate its annual patterns of power output. So the relationship between the average wind speed and the annual energy output from a wind turbine can be actually described via the left curve. And the standard atmosphere with air density of 1.225 kg per cubic meter. And for each of the Weibull shape parameters k to 1.52 and 2.5, and the annual energy output is computed at different average wind speeds at the turbine height. Okay. So based on different wind speed density and at different wind speed records, we're able to compute the annual turbine output via this figure. So this is a very interesting curve. So this different K indicates different Weibull distribution for describing the wind density in terms of PDF and CDF. Okay. So depending on the value of the shape parameters K, the energy output may vary up to 50% at a low average wind speed of 4.5 meters per second based on this figure. Okay. And some 30% at a higher average wind speed of 10 meters per second. Okay. So 10 meters per second. So the variation can be 30%. Okay. So based on the left figure, we can see that consider the red curve with a shape parameter k equal to 2, normally shown by manufacturers. Manufacturers typically consider the Weibull distribution modeling the density of the wind speed with a setting k equal to 2. And for an average wind speed of 4.5 meters per second, the turbines generates about 0.5 gigawatt hour per year. Okay. But for an average wind speed to 9 meters per second, we will reach 2.4 gigawatt hour per year. Okay. So that's doubling the average wind. The energy output increased 4.8 times, almost five times. So if you can see that the importance of finding a good location to set up the wind farm project. Okay. If you are able to find out a location with average wind resources to 9 meters per second per year, and your project will be very successful. Okay. The lower wind speed doesn't mean a linear decreasing of the economic return. It's a kind of, many times decreased. Okay, 5 times decreased. So the output of the wind power actually varies with wind speed. For the average speeds, 5 and 10 meters per second, energy output will differ by the factor of 4. So the reason for the difference is that the efficiency of the wind turbine varies with the wind speed. Okay. And also the uncertainty that applies to the power curve also applies to the above results. And the calculations can be refined by considering that the temperature climates, the wind tends to be stronger in winter than in summer, and stronger during the daytime than at night. Okay. There's another very interesting metric that we can utilize to evaluate the capacity, okay, based on the data, which is called capacity factor, turbine capacity factor. It is the ratio between the actual annual energy output of the turbine and the theoretical maximum output. So theoretical maximum output is deterministic. So you may, under assumption that the turbine can be running for like a full year without any shutdown, which is 8,766 hours. Okay, then for 600 kW turbine producing 1.5 million kWh per year, its capacity factor will be computed as this. Okay. So it's 8,766 hours per year multiplied 6 kW. 6 kW is the maximum capacity of that turbine. And the total amount is like this. Then we can compute the capacity is 28.5%. So capacity factor may theoretically vary from 0 to 100%, but in practice, it usually varies from 20 to 70%. Okay. Another dimension of metric to evaluate the data we collected from wind farm is called turbine or wind plant availability factor. Okay. This availability factor is a ratio between the turbine plant, the time that turbine plant is available, and the total time. Okay. This indicates the gap or the duration that the turbines are not operating, and it will, to some extent, reflect the management performance on those distributed machines. Okay. So we can compare the three metrics: the turbine power coefficient, turbine capacity factor, and the availability factor, for evaluating the wind power generation performance. Okay. Next, let's look at some power curve model based on the data-driven aspects. Okay. So given the real data we obtained, which has one dimension wind speed, another is electric power, we can actually draw the wind power curve by plot the scatter diagram of that data. Okay. But if you can see that if we plot 10 minutes data and plot the 1 minute data, 1 minute average data, we can see that the power curve shape can be changed a little bit. Okay. So in 1 minute data, some of the data points, so probably will cluster here. The most chance will be clustered here. Some other data places, the data points are pretty scarce. Okay. And the 10-second data, you can see that they're dispersed even more. Okay. So that means the average actually reduce some of the information. Okay. So if we average data points to a longer time scale, a lot of information is lost. Okay. Especially a lot of variations is lost. So to model the shape of the scattered diagram plot here between wind speed and power, we have a number of choices. First, we can use a linear power curve function to do a linear fitting of this power curve. Okay, so it's a stepwise linear function. So it has a constraint that if the wind speed less than cut-in, then it will be 0, the power will be 0. If the wind speed is higher than the rated but less than the cutout, it will be to its maximum capacity. But if it is within the Cartesian radius, it will be a linear curve, okay, like this, lambda multiplying the wind speed plus this one, okay, which is the slope, intercept, okay. The lambda is the slope. We can also do a linear square fit, or least square fit by a more complicated machine learning model, okay, or kind of non-parametric power curve functions to make a more flexible curvature than the linear stepwise function. And the third way is using the k-nearest neighbor algorithm. So the k-nearest neighbor algorithm is actually research the nearest data points, okay, among these all data points and compute the average, okay. Then we will have such kind of, it will be more dynamics, okay, more adaptive to the shape. Okay. All right, so we probably stop here today. We will talk the data-driven model by extending the power curve model next time. All right, thank you very much, guys, for listening today. So I will see you guys next week. Thank you very much. Bye-bye.